So good morning, everybody. First, I would like to thank you, the organizer, for inviting me here and present all the work we have done in Villeneuve, in particular about all the infrastructure that we have developed to run high-throughput workflows for Abinit. And so, to begin with, usually when you start and present high throughput for DFT, the first thing I would probably talk about would be why it's interesting to run high throughput calculation for DFT, and several reasons. Or maybe what is automation, what is a workflow, how it is useful for our research. But I guess that both of these topics have been covered to a large extent in the past days. So I would rather to address another kind of problem, and it is how we do that. So what I hope is that I will be able to give you a bit of a different perspective, because the code that we have developed is definitely not AIDA. I think there are several differences. I'm not an expert in the usage of AIDA, so I will not maybe be able to make a complete comparison, but I will try to highlight maybe some of the differences. And what basically I will show what is needed, what details about the implementations, and what were the problems that we encountered, and maybe that it will be hopefully useful for you when you develop a new workflow or maybe a new plugin for AIDA. So to give a bit of context about how this whole project came to be, the first thing is that, okay, so all the development was done, well, almost all the development was done in Villeneuve. And let's say that the main target of our work was to bring Abinit to the high throughput regime, and in particular to add support for let's say advanced kind of calculation like DFT that have a lot of subtleties to run. And the final aim of the project was to run phonon calculations that would have been added to the materials project. And this is a bit of a timeline, just to give an idea of the time that it took for us to come to something stable, more or less. First development beginning of 2013. Then I joined the group in 2014, and we started developing the infrastructure for the high throughput. The first package we started developing was this AbiPy, which is a Python interface for Abinit, and then we moved to developing another package, a different one that contains the workflows, that is called AbiFlows. And it took basically a couple of years to design and put together all the pieces, start running the calculation, and then collecting results and publishing them. Now we are basically in a situation where we are sort of stable and we keep adding features, but we are satisfied with the current version of the workflows. So as I said, this is more or less the plan of what I plan to talk about. So first, actually the high throughput infrastructure that we have developed, then focus a bit on the workflows and the problems that we have encountered developing them. And then I will shortly present the results about the high throughput phonon calculations for which we used our infrastructure. So to begin with, I would like to mention all the pieces that are needed to run a high throughput calculation. So to give an idea of what is under the hood and what is actually needed and the efforts that have been devoted to that. So I will try to go through all the different parts that are needed, and I will already highlight one difference from AIDA here, that all the things are, all the frameworks are developed in Python, but instead of developing the whole ecosystem, we try to reuse different frameworks as much as possible to benefit from developments from other groups. So the first step is the DFT code. This is relatively trivial. It's Abinit, as I said in the beginning, but there is one important thing that I would like to mention, and is that since the development of Abinit started in Louvain-la-Neuve, we have a couple of core developers in our group. It's a big advantage for us because we have the ability to modify also the source code of the DFT part to directly interact with the, not directly, but to interact more easily with the Python code. I've been done developments for development of workflows for different other DFT codes, and actually the communication of the information between the DFT and Python is usually a big challenge, because one has to go through text files, parsing strings, and this is a big issue and considerable waste of time. So in this case, we managed to take advantage of our direct connection with the Abinit development. So this covers the DFT part. Now, for the inputs, when you generate an input, you basically start from a structure. For this, we rely entirely on the Primagen structure. I guess this was mentioned in the last days, so I will not spend much time on this. Just mention that we have, having a connection with the materials project, we have some tools that are available in Primagen that ease the interface with Abinit directly. But let's say this is for the first thing that you provide to a calculation, being the structure, your crystal structure. Then the next point that you want to address are the pseudopotentials. I guess this is probably being dealt with in a previous talk. I think that was Stefan Cotonnier. I guess he described all the delta factor. So I will not repeat any of these topics. But I will mention that our group was involved with the within the delta factor effort to provide high quality pseudopotentials, because these are crucial to run high throughput calculation in an automated way, mainly because one was calculations that are accurate, but that one does want to have also suggested values for the cutoff, mainly, so that one does not have to care to make a long convergence study about that, and a direct integration with the Python code. This was done in the pseudo-dojo project, which is a table of pseudopotentials that are available even in the quantum espresso format, and this was a huge advance compared to all the pseudopotentials that were available on the Abinit website, who have a terrible delta factor, as you can see, and now the green line is the current version of the pseudopotentials that are in line with all the other tables that are available at the moment. This was very time-consuming, all these two parts, but were part of a different effort. Then it comes the full input in the input file that you want to provide to the code. And this, again, this is text, and it should be formatted in a way that the code can pass, and it's somewhat quite time-consuming to develop such a thing, even if it's not too complicated. This is implemented in the AbiPy package that I mentioned in the beginning. And the object itself, it's not something very complicated to deal with the input. It's basically a dictionary of variables and the values in the Abinit code. But we went to some step further and we made this object easily usable to interact directly with Abinit to get some useful information, like what will be the number of k and which are the k points in the Boolean, the reducible Boolean zone. Just to mention a few examples and the list of irreducible perturbations, so that we rely on what will actually be calculated. The point is that, as I've said, this is sort of dictionary with the values, and this is good and fine when you want to define some standard or input for the very beginning, but you have your let's say system that you know, but when you run high throughput, then all sort of structures and approximations might come in, and the simple object is not enough. So basically, we developed what we've called factory functions for the inputs, so that we have a very basic minimal input that we provide. In principle, one can just stick to the structure and pseudopotentials, and then define a series of meta variables, like, for example, the density of k points instead of giving the explicit grid, to cover most of the possible cases that might come up, and deal with the high throughput computations. So in particular, this is an example of a factory function, and you can see there are basically the only compulsory values are the structure and pseudopotential, and then there are all several values that can be set. So this is good, but already brings me to two main problems that one has to deal with. One is the balance between the flexibility that you want to have. I want to set, want to do all kinds of calculations, and the usability of the interface that you develop. This has been, a matter of discussion in our group when we develop something new, because to me, it's always difficult to say, oh yes, I can provide something that covers most of the cases that the user wants, and then someone comes up and say, no, but I wanted to do also this kind of calculation that is maybe not managed by the function. And on the other hand, I would sort of say that this is a function with a certain amount of parameters, and it's for a relatively simple calculation. And one would say that one does not want to have functions with 100 parameters, otherwise you go back to the original situation where you just have the full input. And the second problem is that you have to define default values, and this is another tricky part, and I will come back to this later in the talk. So this addresses the part of the input. Now, further handling, which is definitely needed for an automated calculation, because you don't want to go inside your folders and fix all the errors that you encounter. You need something to fix automatically the problems. So for this, I will not enter into many details, but the interesting thing is that, to me, is that we managed to actually take full advantage, as I've said, of the being developers of the Abinit code. So we basically use directly at the Abinit level YAML and the netcdf files to directly write the errors in a format that could be parsed by the Python code. This is very convenient, because as I've said, in other codes, the only way is to just make some parses of the text files, identifying strings, hoping to get the right error message, maybe make some guess and cross checks, and this is a lengthy process of fine-tuning. This helps us a lot to reduce the amount of time we spend on this. And also this is very convenient because this is a sort of a iterative procedure defining of errors and ways to handle them. So basically you run simulation, you find an error, and then you try to find a way to fix it, and you may fix it at the level of the implementation, but on the other hand, we had a few cases where the errors obtained in the high-throughput calculations also allowed us to fix error directly in the DFT code. So this is a double advantage that you have from running and being in this process of trying to find automated corrections. So this is for the handling. For the database, that's in which we store the results. This, I'm pretty sure, is a opposite choice with respect to AIDA, which, as far as I know, is based on SQL. Instead, we decided to use MongoDB, which is a non-SQL database, meaning it's based on documents. And we use MongoDB and Mongo Engine, which is a document object mapper, which is basically the equivalent of a relational object mapper, but for document-based databases. So I will not enter in the technical details of what's exactly MongoDB and why maybe we decided this. The idea that we had was to write our own objects for the Mongo Engine framework. In order to standardize the keywords that are stored in the database between the different users and all the different workflows. And this was to ease the sharing of the results in our group and hopefully outside of it. And the other point is that being the MongoDB based on a document, we decided to just store there only quantities that you might be interesting to filter, to query. Not stick with all the outputs there, but still make them available. So, as I've said, part of the outputs of Abinit are stored in netcdf files, and we store those in the database so that we can directly access them from different points from our machines, from the clusters directly, and these are contains usually the true output, the true quantities in the output that you want to interact with, but that you are not supposed to query. Nobody wants to query the database for the third the energy of the third band on the second key point. So it's sort of pointless of having in the database. So. Sort of last point for the workflows is the workflows management. So as have been already said, this is based on frameworks that was developed at the materials project. We gave some contributes to it. I will spend just a few words saying that this is a completely general workflow manager. It's not tied in any way to DFT calculations. So it's quite flexible, and still one has to implement all the logic which is related to the DFT calculation. So one has to implement what are called the tasks inside this framework and put them together. I will maybe spend more time when describing the workflows. And well, as a last point, the analysis of the data when you have collected thousands of calculations, you want an easy way that is easy to interface and then get your results quickly. plotted or analyzed, and so we have developed all sort of post-processing tools inside AbiPi so that you can directly access the netcdf files either from the file system, so even if you have simple calculation, or directly from the database, access the netcdf files and plot them in all sort of things that you can think about. So this sort of concludes the list of things that were needed, and these were the frameworks that we had to think about when we were sitting in the beginning in 2014 and trying to figure out what was needed to actually run high-throughput calculations. This was anyway sort of process of trial and error, but I hope I at least gave you the feeling that it was a somewhat complicated process and a lot of parts that are involved in this process. So next thing is actually to address the workflows that we have developed. For this, I would like to spend a few more words on the framework, because I think here there are quite some differences with AIDA. So the first thing is that there is basically no central point that controls the calculation. As far as I've seen, in AIDA you have some you have your interface, and this connects to the cluster, checks the state of the calculations, and makes the workflow evolve. Fireworks works in a sort of opposite way. Basically, there is the database, which is a central point, but it just contains the information of the current status of all the calculation. But there is no, let's say, central intelligent point that goes through all the calculation and oversees them. Rather, it's the user that, when creates a new workflow through the tools provided by Fireworks, writes the information on the database, and on the other hand, there is Python code that is running and wrapping the execution of the calculation that fetches the calculation that has to be performed from the database and executes it. And when the calculation is finished, is the Python code that has been running that updates the status of the database itself. So I think this might be a thing that is important to specify, and so that all the logic has to be implemented at the level of the tasks in Fireworks. So this is basically what we did with the AbiFlows package. We implemented a library of workflows for Abinit. So the problem is that for different kind of calculations, you might need a different kind of logic to connect the different steps of the calculation. And our idea was to make it as modular as possible, so that we had several blocks that could be then combined again to generate all sort of workflows. But again, this was something that came sort of a price because you have several kind of calculations. You want to invest some time, make it as flexible as possible to make different kind of workflows. But on the other hand, otherwise it becomes too complicated, and then you are basically writing a new workflow and all new tasks every time. So it's something that should be taken into account. And for always this topic about the flexibility versus the usability of the code, one of the, let's say, of the it's not really an issue, but let's say of the challenges is how to generate the workflow for something that has to be automated, and you do not want to invest a lot of time generating its input. So as I've said before, we rely on the factory functions that are implemented in AbiPi, and we basically have the same kind of input plus all sort of variables that might be needed for the actual execution of the workflow. So this one that is shown here is a fairly simple one. It's just a relaxation. And in any case, I've said before, I would still think that there are many parameters that the new user has to take care of and look at the meaning and the variables. So one has to try to balance these kind of things when writing a new workflow. And also maybe trying to abstract all those quantities that, or let's say all those functionalities that are not really specific to one single workflow but shared among all of them, and we try to have functions that set those properties of the workflow that are not common to that are common to all the workflows from a external let's say external functions that can set these kind of things. So this is a relatively simple example. Then you move to something which is somewhat more complicated. This is the full DFPT workflow that is implemented. So these are more or less all the perturbations that are available with DFPT, not only the phonons, but also the strain, third order derivatives. And one would like to run this kind of workflow and give one single input for all of these. So now necessarily the inputs become more complicated. The factory that you have to provide, you have basically the same inputs as before that I've not put, not to fill the whole slide, but then you have another set of inputs, and I think again here I removed some of them. The idea was to make, as I've said, the thing modular at several levels, so that at least one can create one DFPT workflow, one relaxation workflow that are obtained from building the different, connecting all the different tasks that have to be performed, and then create a new workflow which is the sum of the two. And this is definitely feasible, and I've done it, but on the other hand, here I will pledge the cause that this is not such a good idea. To me, it has been just more complicated to handle something which has several inputs and several kind of outputs. So as a rule of thumb, we have decided that basically now we develop workflows that are, let's say, self-consistent in a sense. So for the let's say DFPT part, we need to start from self-consistent and get to through all the perturbations, and this is not something that you can split up in smaller workflows. But the relaxation and the phonon, yes. And so this is what we did. And I think that the main issues that we had was that when you have a problem inside the phonon part of the workflow, then your structure, the relaxed structure is somewhere, in a sense, and you need to go and recover that unless you have end up with this long workflow that you do not know exactly what has been completed and not, and look into each of them. And then you have to provide a factory function that takes care of all the inputs for the relaxation part and the phonon part in a single place. And I would claim that this is much less user-friendly. So basically, what I usually do and how we usually deal with this is that we split the kind of workflows anyway, and we run in workflows with the relaxation. We store all the results in the database. This is still perfectly fine for us when doing high-throughput calculations. Usually, you do not look at the details of each of those thousands of calculations. You just have your database with all the relaxed structure, and then you can run phonons on all the relaxed structure, electronic band structures as well. And so this is my take on the choice of how to organize the workflows. Another sort of issue that you encounter quite early in the development process of a workflow is the connection of the different steps, and in particular the connection of the files. This might seem a trivial step because each one of us does this daily, and still all the DFT code that have their own subtleties and ways of passing the inputs and changing the conventions. So for example, in Abinit, you cannot just simply, if you need for a non-self-consistent calculation, you need the density from the previous step. It's not like, I don't know, VASP, where you can copy the file. No, unfortunately not. You have to adapt the convention from the output of the previous step to the input, and you cannot just use the same naming of the files. Maybe, or like in the DFT part, you have to fetch files, different files, wave functions, first order derivatives of the wave functions from different calculations. So you have to decide which input you should copy from which previous part of the task. All these things are quite annoying and have to be dealt with when you start developing a new code. Let's say the workflows for a different code. So for this we have adopted a few strategies, let's say. The first thing is to remove any freedom from the user to name the files and decide what they want there. People come and say, oh, I would like to call the files like this. No, you don't do that. You call the way we decided. Anyway, it's not important because the point is exactly that you do not have to go there and look at the files yourself. The whole point of this, but it's difficult for newcomers to stick to this different approach. And then basically we tried to provide basically some convention to define which files we are addressing and leave this customizable, but not having to mention directly each single files, maybe relying on extensions or on references from the other inputs that allows you to identify which are the useful files. Another issue that is usually important, well, let's say that probably the most important thing for high throughput is the stability of the code, the DFT part and the calculations, but speed is an issue as well. And you would like to parallelize your calculations, but okay, there are a lot of things that needs to be checked if you want to do that. There are all sort of parallelization levels, all sort of options, and then maybe you have constraints from different clusters, and there are basically two approaches that one can take, one easily at least. One is to use the same configuration, same parallel configuration for all your calculations, and you do not really care, or you go into each calculation and try to set meaningful parameters. This is not really feasible when you are running 1,000 workflows. It will take you more time than the time the calculations last. So we tried to automate a bit the parallelization process. Again, we do this relying on Abinit. Basically, we write down a specific input for Abinit, and we run Abinit in a sort of dry mode. And it's Abinit itself that, knowing all the parameters that it is going to use for the calculation that is about to be executed, that tries at least to give some information about the basic level of parallelization. This is at least the number of K points, the number of FFT grids, number of bands. These are known at runtime for Abinit and can try to make some guess. So this is interesting for us, and I have been using this for the whole process of running phonon calculations. I would say I'm satisfied with the basic level of parallelization, but in some cases I've also seen something which is completely off. So it's something that should be used with a bit of care, and there are definitely room for improvement, and maybe even within the community, something that could be tried to figure out in general about how to define reasonable, good parallelization parameters. Still sticking to the topic of parallelization, another kind of issue is that maybe you have some constraints from your system administrator, the clusters you are running on. So maybe, or maybe you can take better advantage of the machine that you have available. So maybe it happened to me that you need to use, or you are greatly favored if you require for a full node, or maybe a larger number of processes, or maybe it's easier to ask for a longer job. You get some priority in the queue, it depends. So the idea here is not to rely on the parallelization of the code, but rather on the parallelization which is allowed by fireworks natively. Since, as I've said, it's the Python code that is running inside the node and wrapping the DFT calculation, basically what you can do is you can run multiple DFT calculations at the same time. Let's say reserving one full node, 64 cores, but maybe these are too many or do not fit well with your parallelization level, and so instead of running just one DFT calculation, you run 3 of them. Maybe this is not super optimized from a high performance point of view, but still it might be good when you have to run through really a lot of calculations. As I've said, this might be useful when you have some external constraint. For sure, then you have to make some adjustment maybe to your workflow system, because maybe you end up risking hitting the wall time or requiring too much memory. So this has to be taken into account, but yet it's an additional strategy that is available. The last point I would like to mention is the detection and handling of the failures that happen in the code. And here I will distinguish 2 kinds of failures. One are the soft failures, and for which I've mentioned earlier the error handlers that we've implemented. And here again, taking advantage of the fact that there is Python code running and wrapping the DFT calculation, basically we have 2 possibilities to run this error handling procedure. One is to generate a completely new calculation and a new job in the queue when there is an error. So let's say the calculation stopped for some reason, the error is detected, and a new step is created, a new job in the queue is added to the system. Another option would be to fix the error just in time and keep looping until either the calculation is satisfactorily completed, or there is a final error that cannot be fixed. Again, this is something that you could take advantage when you have different constraints in your system. Like in one case, you might have let's say this happened, like, oh, the system administrators want you to run the calculation on the Scratch system, and if you keep running on the same job, you avoid a lot of I/O, copying your files back to the project folder and then copying it back to the Scratch folder. While on the other hand, for example, in this approach of looping, it might be easier to end up hitting the wall time, or you lose a bit of traceability, or if an error happens maybe in a later point of the calculation where several errors has already been fixed, basically you do not have a point to recover at a previous step. So there are, again, pros and cons from both the perspectives, and one has to try to see which approach fits better to his or her own use case. And the other kind of failures that I've mentioned are hard failures. These, I guess, again, everybody has faced them. And I refer to a hard failure when your job is killed in a hard way by the queue manager. For this, there are all kinds of potential causes for this. This could be caused because you are hitting the wall time, you did not ask for enough memory, or maybe simple, it was a hiccup of the cluster and it decided that your calculation needs to be killed and it's killed. And then what do? This is somewhat slightly more complicated to deal with in fireworks, since as I've said, it's the Python code that is running that updates the database. So the calculation is not, the database is not immediately notified because nobody had the time to tell the database that the calculation was being killed. Still, there are tools to go and check easily that a calculation is actually lost and recover it, but still one has to try to figure out which of the causes are these. We sort of tried that, and this is sort of a negative note in our development, because we have spent quite some time trying to write sort of ad hoc error handlers that could target the different queue managing system and trying to parse which error is given for if there is a memory error, wall time error. But we implemented on a couple of clusters, and then we moved to another, and it had different error messages. And at some point we realized that we were not able to maintain this kind of thing to be available on an arbitrary cluster. So even if in some cases this was helping us avoiding going in the folders and maybe check what the actual error from the cluster was, I would say that this created more problems than those that it solved. So at some point we decided, we keep the code, but at the moment we are not using it, so a bit sadly. So this concludes a bit my overview of the workflow part and the problems that we have tried to face, and maybe have that could be shared also in the AIDA ecosystem. And the last part, I would like to show the actual application that we made with these workflows. So as I've said, the aim was to run high throughput phonon calculations. Well, I will not enter into the details why it's interesting to have phonons. There are all sorts of properties that you can extract from those, so it's good to have them. But running this workflow in a high throughput manner was supposedly difficult to begin with, so we made all these developments. And then I come to one of the problems that I've mentioned before when I was speaking about the inputs. About the default parameters that you want to give. You have as I've said, all sorts of materials that can come in, and you want to give some input that is decent enough to run your DFT calculations. So basically, you have two potential approaches. One is you make a separate convergence study for each of the material. This could be automated, but requires a lot of calculations in itself. And on the other option, on the other side, is to find sort of good parameters that you hope will be fine for at least most of your calculations. Since we are dealing with high throughput, in a sense, and we say that the main usage for this kind of calculation is for making screening, and then you can maybe go inside the material and make an effort to make a more accurate calculation, it is to us definitely fine to rely on a good set of parameters and just use those for all the calculations. But the question that arises immediately after is, what is the good set of parameters? So as for the cutoffs, as I've said, we rely on the values provided by the pseudo-dojo that have been also tested towards the convergence of phonon frequencies for a set of materials, so that they should be fine. But for example, two things that you want to set, like K points and Q points, these we did not really have a clue about what were the good values. So we made a full convergence study to decide these parameters. And this might be one thing that one wants to address before starting running a large number of calculations. So basically we selected a set of materials, semiconductors in particular, we focused on those. And we tried to be, to take into account different kinds of elements, symmetries, size of the system, gaps, all things that you can think about. And we basically took a very converged calculation with high Q, high K grids that are definitely converged, and then run all the calculations with smaller grids and try to do all sorts of statistics on the mean error, maximum error, relative error, absolute error. This allows you to tune your calculations based on the actual quantities that you want to obtain, like the phonon frequencies, the Born effective charges, the electric tensor, that are all outcome of the workflow. So we wanted to make sure that these were reasonably converged. So in the end we came up with a number which is a density of K and Q points, which is 1,500 points per reciprocal atom. If you have no clue, this basically means that once you have the number of K points multiplied by the number of atoms in your cell, this should be roughly 1,500. To be fair, this is quite already good converged calculations. I did not find a material that was very badly converged with this, but doing the convergence study also came up with a few more hints about what would be good to choose as a grid. For example, we always use commensurable K point and Q point grids, obtaining a smoother behavior close to gamma. And we also observed that the convergence rate is way better if we stick to K points that respects the symmetries of the system. This might not come as a surprise, but when you generate the inputs automatically, it might be that you get something that does not respect the symmetry. And then in the end, we also made some sort of validation towards the experimental results, because yeah, of course, we could have made something very converged to the wrong value, and then it's not really a very good parameter. And we compared these with experimental data for the vibrational entropies, gamma frequencies at gamma, for the available data in literature, and I would say that all of those are completely within the expectation of the DFT calculations that you can do, and in agreement with previous results in the literature. So, after having spent years implementing all the tools and running this convergence study, then we finally moved to the real calculations. So we've run these 1,500 roughly. Now, actually, this was the published data. Now we are keep running them, and there are roughly 2,000 now, and still to well, it takes time. It takes time. I mean, it's for these 1,500 were roughly 5 million CPU hours, which is not too much, but it's not such a small number still. And for these, the data are published with the full interatomic force constants available and some post-process data. The same data are available on the website of the materials project and through the REST service. Sorry. And in particular, also I would like to cite these. You can also visualize the modes of the phonons using this phonon website tool that I guess is the same that is implemented in Materials Cloud. I wanted to mention because this was done by a colleague of mine, Enrico Miranda, who did a very nice job. And so basically, once you have run all these calculations, you can even spend some time making an assessment of sort of the quality of your work. So I think this is interesting because you go back and see if the workflows were fine and the approximations that you took were fine. So we basically looked into all the workflows and checked in our database how many calculations I was perfectly aware how many calculations were not completed, and I would say roughly only 30 did not complete at all, even after maybe some human intervention. And if you look at the reasons, these are all completely fine. I mean, there's some structure was taking too long to relax, or maybe I'm not entering the details, but maybe not a good choice of the structures to begin with, or some elements is actually maybe the pseudopotential was not as good as the others. So for the workflow part, I would say we were satisfied. For the numerical part, we tried to make a assessment on our results and try to add warnings to our database of calculation based maybe on the presence of some small negative modes close to gamma that usually signals something not very well converged, or maybe making some statistic on the breaking of the sum rules in the phonon calculations, and try to point out those for which it might be too large, and so if one is interested would probably need somewhat higher cutoffs or stricter parameters. And then finally we also tried to look at the k-point grades to see if our, let's say, the Q-points grade, sorry, if our convergence study was fine. So when you have a certain grade, you can basically use subgrades to recalculate the same phonon frequencies, and then you can compare with the one with the full set of Q points and see the errors. And if you manage to look at a grade which is not too small compared to the original one, we would say it's the average error is relatively small, but there was some discussion, for example, in our group, your calculations are too well converged, we can use half of the Q points that you claim, but basically not. Okay, so we made all this kind of study to say that no, we actually think that we did a decent job in selecting the parameters. So with this, I basically conclude my talk. I would like to thank all the people that have worked on these implementation and calculations, both in our group and at the materials project that have helped us. And of course, thank you for your attention.
Thank you very much. It's quite interesting. Are there any questions?
So, the net-linear format was created for weather simulation application.
Yeah.
And you're using now for material simulations.
Yeah.
And back in Colombia, the mine is using for Monte Carlo simulations of magnetic materials, and it's quite successful. So for high-throughput simulations, sometimes you want your simulation to run in a very basic machine that probably is not even connected to the same network as your, let's say, drivers NetCDF has some network, like you can write over the network to a NetCDF file. Have you explored the possibility of like having the NetCDF file in your main server cluster or your own laptop or object store, and then writing from the machine that is running the simulation?
Okay, this is the technical question concerning Abinit mainly. And this is a matter of discussion inside the group because the support for the NetCDF file is not complete, in the sense that there are several versions of NetCDF, and HDF5 also. So the point is that there is support inside Abinit, but this is usually difficult to have it work in the proper way. So inside Abinit, there is a fallback for the NetCDF that works with the version of NetCDF 3, basically. Then, of course, you can interface with the libraries on the cluster, and try to have some good NetCDF 4, HDF5 working, but this is usually more work. And the main concern and the main discussions at the Abinit developers meeting is, yes, it's all very interesting, but then the user comes and say, oh, I cannot compile Abinit. And this is the main issue that this was one of the things that were discussed. The users are complaining that is difficult, so this would add one more difficulty to the task. So yeah, this is something that could be addressed, but already having this working in a stable way is difficult enough, and that's what we are focusing on. Yeah.
So, thank you, Guido, for this presentation and really for adapting it to this workshop. We really appreciate it. I'm sure you will get lots of questions during the coffee break. Okay. One thing I wanted to ask is about the process of publishing the data on the materials project. Could you maybe walk us a bit through this process, and also which part of the data is available there, like which metadata, etc. That'd be very interesting.
So basically. It's a multi-step process. First, we run our calculations, and the calculations are stored in the MongoDB with our conventions that we have developed. Then, since they are running other codes, I mean, aside from VASP, they also use Bootstrap, few things like this. Not really high computationally intensive, but then all of these are usually stored in output databases that are usually MongoDB. Then they develop mainly them, and everyone who adds a new workflow and new data, basically they write what are called this builder system. There are a few packages that are available on GitHub and that are used. I mean, they are not really useful for people that are not inside the group, but these are an interface to extract the data in the different formats that, Abinit format or VASP format, and convert them to something that is usable from the web interface, basically. So they usually, let's say, for example, for the phone structures, we store them in the NetCDF files. Then, during this builder process, we convert them to PrimaGen object, which is then stored in another another database, and this is directly accessible from, for example, the REST server. So there is this web interface, and we directly store there maybe the figure obtained from the calculation, which is accessed by the website. And I know for the phone website, we preserve for a subset of the Q points in the path the eigenvalues and eigenvectors, so that we can make the oscillations and stuff like this. And then, of course, there is all the technical people that will live with, like Donny Winston. You have met him. So he's mainly in charge of doing this. Then, I mean, we try to. I mean, it's a bit tricky, all this thing, because we need to go through maybe when we want to add a new property that we are in the process of doing, then we have to implement new objects in Pymagen, having those merged, and it's not always an easy task. And then when everybody is happy, you maybe rerun your builder and prepare all the new quantities post-process that are then available directly on the website. This is my view of. I hope I answered your question.
Hi. So thank you very much for the nice talk. I have two questions. One is about this key point per atom parameter.
Mm-hmm.
First of all, do you know, is it transferable to other codes or it's only for Abinit?
I would say this is transferable to other codes.
And then, if it is transferable, let's say we take CP2K. So, I mean, if I would take a unit cell and then just the number of key points, I would just, that's easy, right? I just take the number of atoms and multiply the number of key points, and then I get a number. But if I increase the unit cell, so I will say I will also increase the number of atoms per cell and also the key points intrinsically, right? So, how do I do in this case? I still multiply the number of atoms by the number of intrinsic units, K points somehow? Or?
Okay, this is a good question. Okay, so there are 2 points here. I hope I got your question right. So, for example, if you want to, let's say, calculate a defect and you add one atom to your cell, for example, in that case, what we do in a situation like this, we keep. We first define in the initial workflow what is the reference K point, and then we keep it through the same through all the other steps that are needed. Let's say if you want to calculate add some 1 or 2 atoms and to calculate it as a defect, you want to make a difference in the energies that is compatible, so you need to have the same number of K points, so it will be slightly different. And to this, the point is that it would have been a better choice, in a sense, to use a density per volume. This would be definitely more reasonable as a choice. The problem is that when you start from maybe an experimental structure or even a structure that was relaxed with a different code, you relax the volume and the volume changes. So what do? You do the relaxation, you start with a density of K points, then the volume changes and the density of K points is not the same as the one you began with. So you can either iterate this process up to a convergence where the density stays the same, but this seemed a bit of intricate machinery that was a bit error prone. So we stick to this density of points per reciprocal atom that was basically the thing that used at the materials project. So basically the answer is that to me it would have, for if you need to deal with changing the number of atoms, it would have been better to have something based on the volume, but it was not easily achievable.
Okay, so the second question is about the complexity of the workflows.
Mm-hmm.
So, in AIDA, it was actually suggested to have this hierarchy of workflows, and you kind of.
Suggest.
In AIDA, when was it before yesterday, there was a talk, and then it was suggested actually to use a hierarchy of the workflows. So, one workflow calls another workflow. What I understand from your slide, it's not really it's not a good approach. Can you please comment on this?
Sure. I think, I was a bit afraid of this point, because I think this boils down to the differences in AIDA and our system. The point is that in AIDA, everything is integrated, so you have your central database as far as I know, and the control of the workflow is the control of the results as well. This is a unified process. In our case, Fireworks is the workflow manager. And dealing with an increasingly complex workflow is increases with some power of the number of steps in the workflow, the complexity of dealing with it. So I'm not sure whether this is truly an issue for the AIDA approach. This is definitely true in our case, because basically you run all your workflow and you control it from the database. But what we have then is the results stored in another database or in another collection of our database, and having let's say the advantage of dividing your procedure in several steps helps us a lot to keep the things under control. So since I guess in AIDA then you always in your sub workflows come back to the same database, maybe it's easier to deal with these kind of things. But still, when you are running thousands of calculations, I feel that you would not want to look into anything, and I would like to have still my final collection with all the relaxed structures, and another collection with all the phonon band structure, and another collection with all the electronic band structures. And these, at least in our case, is much easily achievable when splitting the workflows. So I think it's very, if I were to make a quasi-harmonic approximation calculation, when I do a quasi-harmonic approximation calculation, if I have to work on one material, I would probably like to have something that does the whole thing. It finds the volumes and 5 different workflow for the phonons, and then gathers all the results and make the statistics. But when I do that for, let's say I did for a few hundreds of materials, still, it was completely fine to have in my database all the phonon band structures calculated at different volumes and make a post-processing afterwards. And I'm pretty sure that if in a workflow with 5,000 steps, one goes wrong, and I don't have an easy way to store in the database all the final outputs of all the big chunks that have merged together, the easiest way at that point, if there is some blocking error, is to rerun the whole workflow.